Yes. Hello, everyone. Am I audible to all of you? Please write quick yes in the chat box so I can confirm once. Okay. Hello, everyone. So, welcome to the Inter IIT Competitive Programming Conclave, IICPC, and we are thrilled to have you all here today. And we are allied competitive programmers and developers from over 40 plus universities like IITs, triple IITs, NITs, and BEATS, and many other great universities. And our mission is to ignite passion and interest in competitive programming. And we offer support and beginner friendly environment to for your growth. And we are excited to introduce our gold sponsor, which is Algozenith. And Algozenith stands as India's premier platform for internship and placements preparation, and specially designed to help students crack a high-end product-based companies. And their comprehensive preparation programs cover data structures, development, competitive programming, resume building. So you can go there and check those things. And Algozenith is special because of the founder, Vivek Gupta, who is also a great competitive programmer, and uh, he also took first lecture of the IICPC, which was on dynamic programming. You can also watch that. And the other gold sponsor of ours is 0xPPL, and 0xPPL is the next generation crypto and Web3 platform, which is founded by Prasanna Shankar, who also founded Rippling, which was the 1 billion plus dollar company. And he was also a great competitive programmer and he was rank one in India at top coder in ICPC and Google Code Jam. And he hired many to try opportunities in 0xPPL and you are interested in startups, then you can reach out to Prasanna by prasanna at 0xppl.com to connect. And so to our session, so to our session is based on range queries, and Apurva sir will take the session, and he is also a grandmaster at Codeforces and great CPR, and he also took one lecture earlier on range queries, and he will continue it today. So I'm now handing over to the Apurva sir.
Okay, thank you, Dhruvil. Hello, everyone. So, am I audible to everyone? Okay, if I am audible, can you just please write like yes or hello? Okay, thank you, Vijay. Okay, so today our agenda is mainly to go over Fenwick trees and sparse tables. So we did segment tree last time. So there's nothing that a Fenwick tree can do that segment tree cannot do. But we still need Fenwick tree because sometimes that when you need to cheese some problems, like you have some like a pretty bad time complexity or something like that, then you can just cheese using Fenwick tree because it has a better constant factor than segment tree in many cases, and you can also implement it very fast if you want to implement it in live contests. Even I mean, I can just say that even if you are doing some OAs and you need to implement segmentary from scratch and you cannot and especially it's not allowed to copy paste in OAs, but so you can write Fenwick tree very fast. It's like 3 to 4 lines of code, and you can. So what's the main structure of Fenwick tree? In Fenwick tree, you can do something like a prefix query, basically. So you can only do prefix query in Fenwick trees, but you can modify these prefix query to do some kind of range query. So for example, if you have a prefix sum query, prefix sum is the most basic Fenwick tree, and it's the like most used Fenwick tree as well. So if you have prefix sum, you can use prefix sum to do the prefix query. And we all know that from the prefix sum lecture before, you might have all seen that for the range L to R, you need to get some. You can do prefix of R minus. It's my. I have not shared screen yet. I'm just telling you the basics right now. Then I'll share the screen and we will start the actual lecture. Okay, so maybe I'll just share the screen right now so that you are more comfortable. Okay. My screen visible to everyone, right? Give me a yes if it is. Yes, yes, yes. Screen is visible. So from before, we know that the range of like sum of L to R, you can just do query something like prefix of L minus R minus prefix of L minus 1. So this is very standard query if you need to do some kind of range query. So you can do this using Fenwick trees as well. So Fenwick tree mainly support prefix query. Mainly support prefix query. So why are Fenwick trees better? Query. So not better in the sense that they are better than segment tree, but where is their use case? If you can use segment tree everywhere, why not just use segment tree everywhere? So smaller code. So for me, it would take me around like 1 minute maybe to write entire Fenwick tree, and it will take me around 5 to 10 minutes maybe to write entire segment tree myself. So you see, this is a very big difference. I mean, if even if it does not take me 5 minutes, it will still take me like much more time than writing a Fenwick tree myself. Fenwick tree is that easy to write. But again, it's easy to write, but I think it is a bit more harder to understand. And also, I will mention here that Fenwick tree takes only big O of n memory. It only takes n memory. Like if you have 1 to n elements, then it will only take n memory for n elements. Where segment tree, in best case, it takes 2n memory. But we know that it takes like more than 2n memory in many cases. You can implement segment tree with 2n memory, but again, it's not easy to implement at all. You have to write like for and general case you write segment tree with 4n memories, but it only takes n memory. So it's better here as well. So and of course the better constant here because it's completely iterative. Again, you can write iterative segment tree. I'm not saying that you cannot write iterative segment tree. Many of you might bash me that iterative segment tree exists, but it's much harder to write and it's not practical to write in contest. Even if you are like in a 5 hour contest, it's not practical to write iterative segment tree because recursive one is much easier to write, in my opinion. Maybe some people can learn like recursive, but still, I feel that Fenwick tree edges in especially implementation. And I think maybe we can do a quick maybe we can do a stopwatch to see the implementation time of Fenwick tree, how much I take to implement again. So here, now let's start with Fenwick tree. So what's the idea of Fenwick trees? Okay, tree. Okay, so what's the idea of Fenwick trees? So Fenwick trees, I think, have a very basic idea that suppose your number is 1, then what is the greatest power of 2 that divides 1? It's 1 itself, 2 ki power 0, right? So it will only it will only have information about one element. Okay. Then 2, what's the greatest power 2 that divides 2? It's 2 itself. So it will have information about the two elements, right? What's the greatest power of 3? It will have information about one element. 4, it will have information about four elements. And of course, the previous four elements, not the four after him or some standard range, the one that ends at this index as well. So for example, and similarly for 5 and 6, they will have information about them and this, right? Maybe some of you might be able to visualize the query part right now as well, but again, we will see how we actually query the prefix sum here. So for example, you have 6 elements and just give me any array of size 6, and please, unlike last time, don't give me 2-digit numbers. We all saw that last time I failed to add even 1-digit numbers. For 3, it's not the same. The largest power of 2 that divides 3. What is the largest power of 2 that divides 3? Okay, this array looks very interesting to me. 3, 5, 6, 8, 1. Again, just I said to give me an array, just don't give me 1, 2, 3, 4, 6, 8. What was that? 3, 5, 6, 8, 9, 1. Right. I can still do some addition. I haven't failed enough yet. So for information about for 3, what's the greatest power of 2 that divides 3? Okay, it was 1. So 3 will have only information about one element. This shows the range of 3. This shows the range of 4. So where it ends shows the range of the element. Okay, 5 has the greatest power of 2 that divides 5 is 1. So it will have information about one element. The greatest power of 2, here it's important. The greatest power of 2. The another name for Fenwick tree is binary indexed tree. You can see here why it is named such, binary indexed. Okay, so the greatest so 5 divides 1 and 6 is 2, right? Give me a yes if you understood it. You see, if you don't give me a yes or a no, I just assume that it's a yes. Okay. So 1, 2, 3, 4, 5, 6. Then again, can somebody? Okay. So as we all know, I am pretty bad at addition. So I will ask all of you to give me an array, Fenwick tree array, for this range, if somebody wants to give me. So the biggest power of 2 that divides 4 is 4 itself, right? So it has 4 elements. The biggest power of 8 is 8. So previous 4 elements are, you guys also have a very much skill issue in adding numbers. So can you 1, 1, 2, 4, 1, 1? No. Okay, okay, no, I wasn't saying that. It was 1. It was not. It is 1, 2, 3, 8, 6, 22, 9, 10. Okay, let's verify that. I assume that it's true. I believe in you. 3, 8, 6, 8 plus 6, 14 plus 8, 22, 9, 10. Right. Okay. You get a toffee. You can buy yourself one. Okay. So here's the array. So for example, if I want to get a prefix sum of this range, suppose first 5 elements. Okay. So what I can do is, what information does 5 entails? 5 entails the information about one element. So I can take this one element and go before 5. Now, what information does 4 entails? 4 entails the information on last 4 elements. I can take those 4 elements and go before that, and my array is ended. So I get the prefix sum of 5 this way. Like for 5, the answer I got 9. For 4, I got 22. 22 plus 9 is 31. And you can confirm that the sum of these elements are 31. Do you think this is magic? Like binary magic? I think there have been many blogs about. Okay, so anybody who understood this can say yes. We will go over how this works now, but anybody who understood it can give me a good yes. Okay, so the sum is 31. So how this works exactly is for each index, I can let's look at its binary representation once. Okay, if you look at its binary representation, the thing becomes very much easier. So for 1 to 6, we can keep 3 digits of binary representation. So 001, 010, 011, 100, 101, and 110. Okay. So what happens is if I need a prefix sum of this, okay. So what I need is I need this bit number, right? These many numbers I need na answer for. It will be very easy because you only look at every bit. I will give you an idea how it comes out to be log n, but let's just give you an idea how you get the entire sum. Okay, so these are the 3 bits for the 5. So what happens is I take the number of elements for this bit here before this number, right? And so before this number, I take these bits. Then when I erase it, I remove this bit. For example, I remove this bit, I make it 0. Okay. Now I need answer for this many 10. So now I had 101. I took this many numbers. Now for this many numbers. Now I need answer for 100. Then smallest bit here is 1. I need value for this many numbers, and I will get this many numbers value, and I can go 000. And when I reach 0, I have no numbers left to be taken. So you guys understood it or not? What was the information we were storing at each index? The smallest bit information. So for 101, the information was one element before it. Now I take this one element and I say that now this many elements, I remove them. Okay. So now I need information for 100 elements and the first 100 elements at that. Got it, right? Okay, I'll explain it again. So for 5, here 5, we needed this element and this element. So what exactly was happening here was 101. So I need this element. So what I'm doing is I'm taking the minimum bit. So actually I need 2 ki power x plus 2 ki power y elements here. Okay, 2 ki power 3, 2, sorry, plus 2 ki power 0 elements here. So first 2 ki power 0 elements were at this index itself, right? That's how we created it. I'm not telling you how we created this, but we have this right now. Okay. So we need this elements. And now if I remove this, I take first these elements. If I remove this, then I have taken this many elements already. And now I'm here. Now I need this elements. And this is nothing but just removing this bit. So is it still not clear to anyone? If it is clear, say yes. If it is not clear, say no. If you say nothing, I go ahead. Okay, I'll go ahead. Now, the thing is, now we understand query, but how do we do everything like this in Big O of 1? Because for the smallest bit, you can do log n operations, right? To get the smallest bit. There is now this comes down to the binary magic. Now, if you do, if I think any of you has heard this, okay, I was writing over it. So if any of you have heard it, then I will just tell you for x, the smallest 2 key power that divides x is x and minus x. Has any of you seen it? So x and minus x gives the smallest 2 key power. For 6, it is 2. For 8, it is 8. For 9, it is 1. X and minus x. It is the greatest power of 2. You have not seen it. So you will not see it, but you can remember this. But I will tell you how this happens. So negative numbers, if is any of you ECE student, any ECE student here? Give me a big cheer. Yes. If any of you is ECE student. Yes, N and minus N. If is any of you ECE student here? Like just asking. Yes, you are ECE student. So you have heard that the negative numbers are stored as 2's complement, right? If you have heard that, give me a 2's complement. Like there are too many yes here. So give me a 2. Like if you have heard that, yes, 2's complement, right? So how is 2's complement created? Like I think many EC students have solved it on pen and paper, how they created 2's complement. Yes. So many students might have solved it on pen and paper, how they created 2's complement. But when you create a 2's complement of any number and you see that what is 2's complement, let me give you a glimpse here. Okay. So suppose our number was 101. Okay. So we flip every bit 0, 1, 0, and we add 1 here. We add 1. So it becomes 0, 1, 1. Now, if we AND this, we get 0, 0, 1, which was basically 1. Now, for any other number, let's see 6. It is very interesting. If you look at 2's complement, 1, 1, 0. So, if you flip its bits, it becomes 0, 0, 1. And you add 1 here. So, it becomes 0, 0, 2. I mean, it is 0, 1, 0 because in binary addition, you cannot have, you have base 2. Yes, 1, 0, 0, 1 to 0, 1, 1. Very nice, very nice, Sidhu. And if you AND these values, if you AND these values, flip plus 1, flip plus 1. Right, right, right. If you know 2's complement, you will understand it very nicely. Now, do you all get it? How you got this smallest power of 2? If someone didn't get it yet, give me a yes. Give me no, like you did not get it. Not yes. There are too many yeses in the chat right now. You will still give me yes, right? Okay. Tess. Okay, Tess is different. Okay, so this is it. This is the binary magic of n and minus n. I mean, I think many of you might have thought that this was a spoiler. Like this was something given by like C++ developers to calculate the smallest power of 2 that divides you easily, but they did not do it intentionally. All the all the compilers, all the like machines are created this way to use like 2's complement as negative number. But this is just a very interesting idea from 2's complement if you add something. So n and minus n gives you this. So query can be done easily. Okay. Should I okay. Should I write a code for query? If you want me to write code for query before writing a code for update, give me a yes. Before I explain update. Update is a bit more complicated, I think. Yes, give me a yes. Nobody's giving me a yes. Sad. Okay, yes. Or okay, update first. So I'll explain update first, and then we can do a fun activity of doing like stopwatch to see how fast I can implement it. I don't know. I just said 1 minute on a whim of on like a spur of moment. So okay. So for update, we saw that again. I will create this array 1, 2, 3, 4, 5, 6. So this had this element, this had information about this element, 3 had information about itself, 4 had information about this element, 5 had information about 6, 6 had information about this element. Okay. So which elements have information about 1, 2, and 4? You see, I wrote 1 to 2 and 2 to 4. I did not write 1 to 2 and 1 to 4 because your parent. So we can denote this as some kind of a tree that your parent is 2. 2 holds information about you, but 2's parent also hold information about you. Your ancestor holds information about you. Is this clear to everyone? Give me a big like yay or something. It's too many yeses. I'm I can't like determine which yes is for what what question. Okay, you guys are trolling. Okay, so one whole solution, two whole solution, three, four is also three's parent because a parent can have multiple children, right? And four's parent will be eight, but you will never go to it because it doesn't exist. Because like you are going to something that is out of the range, and so there will be no parent like that. So five parents is six. So when you have to update one, you have to update two, you have to update four. Okay. So you have to. So how do we calculate these parents? Okay. So parent of x is nothing but parent of is nothing but x plus largest power of 2 that divides 6. Why this? Again, so every question should be why this? Why nothing else? Why can't I do something else here? But why can I do this? So again, we will look at something binary for form for a number. Let's look at 5 again because 5 is the most beautiful number ever created to represent something binarily. So if I add 1 here, so 5 stored information about himself. Okay. If I add 1 here, it becomes 110. This element stores information about 5 for sure, right? This element for sure stores information about 5. But between these two elements, there is no element that stores information about 5. I mean, 6 is just next number, so there cannot be any element. But between 2 and 4, we can see that 3 does not store information about 2. It happens. So it happens because of binary matching. So from each index, we start adding numbers one by one, right? And as we go further, we see that no power of 2 is overtaking, is coming close to this until we have added this bit itself. Largest power of 2 that divides you. You have to add that, not next power of 2. It might become next power of 2, but it might not become next power of 2 as well. For example, 0, 1, 1, 3. For 3 did not become next power of 2. It become like next to next power of 2 when you added 1. Because you have to see the pattern here, like what stores information about you. Because it will never come that. So if you make this bit 0 and you said make this bit 1, this you go before this number. You have to go after it. Anybody understood it? Anybody did not understand? Just give me a no if somebody did not understand it. Good. I will explain it again. So what happens is why you can create parent like that is if you have 101 here, for example, then I can add this number 1 and I can get a number 110 that stores information about you as well. And this is the first number that stores information about you. So let's try to think about it more discreetly without 101, something like that. Okay. So we are here and we have 100. I'm just looking at the first bit because that's the bit that's important, right? Now, if I add 1, if I add 2, okay, we will never surpass these bits, right? And your smallest 2 key power itself is less than the number itself. So if you added here anything like 101 or 110, your smallest 2 or 100 even, your smallest 2 key power will never be bigger than you itself. And you are, and you, what are you? What is this number here until here? This number is nothing but until this range. Okay. So that's why you need to add this bit itself so that this becomes 0 and everything below becomes 0. And you have a number that contains you, like that contains this range as well. So you have to contain this range as well. So anybody understood it? I know it's very hard to understand it the first time because it took me a long time to like make it clear in my head that how this is happening actually. It is very confusing because when you look at bits, adding them is not very consistent. Okay, so anybody who is still not clear, give me a no, or I confused everyone else. No comments, then I will believe that I explained very well. I might be the first person to explain Fenwick tree this well. Yes, yes, Abbas. Yes, Abbas Singh. Yeah, it's a bit confusing, but you'll grab it. I think if even if it's not completely clear after this lecture, come to this part again and again. Watch it again and again and try to consume it. And try to write the numbers yourself. Try to write the binary numbers yourself. Try to see the ranges yourself. Okay. Even if it's not completely clear. Okay. Again, I can just try to explain it again if you guys still want. Just say again if you want me to explain it again. It is hard, I know that. It took me a long time to understand it. Again, got confused, right? Okay. So this part, if you see it, okay. So let's say uh, let f of x be the smallest power of 2 that divides x. Okay. Then we know that f of x is less than equal to x. Largest power of 2, sorry. Yeah, Bhas, you summarized it very well. I mean, I think even better than me. So what happens is when you add f of x, okay, this this index is has the greatest power of 2 greater than equal to 2fx. Right? Anybody who thinks that this is wrong and why it could be wrong? Because the thing is, this was this was one. So and everything was zero before me. Yes, because oop, like above me it can be anything else. It is zero, of course, because this is fx. Above me it can be anything. But if I add these two, this will become the sum will get it zero everywhere, and I will carry over, and I will definitely contain my x in range because I contain two fx elements and I am only fx after my element. Everybody understands that, right? Give me a big yes. If everyone understands it, give me a big yes. Yes, yes, yes. Nice, nice. So now I am saying that no element before this, before x plus fx, between x and x plus fx, there will be no element that will contain me. Okay, let's prove it. Okay, there will be no element that will contain me. You guys can see it, right? Can you visualize it that there will be no element that will contain me? If you can't, then it's okay. Binary numbers are hard to visualize. So again, suppose 1 0 0 0. Okay, let's look at only these numbers. Okay, so I am saying that if I add anything between 0 to this number 1 1 1 1, my I won't contain this range. Okay, so let's see that if I add these numbers, no bit will be carried over ever. Yes, no bit here will be carried over. Yes, give me a yes. Yes, yes, yes. Nice, nice. So we can use this property here, right? We can use this property here because because no carryover is taking place from this element, so we can just look at this these are the only element. Yes, yes, right. Abhas Singh, brilliant man. GM potential. Okay, so again, if this is clear to you, how to code it now? The if this was magic to you, the code is even more magic. But again, I have already told you about parent and how I have to go down. So I don't know if it will still look magic to you. So, okay, give so write countdown if you want me to do a countdown before I start implementing, and then I will explain. Write countdown. I mean, I think it will be fun. I don't even know how long I take generally to implement it. Yeah, countdown, countdown. Nice. You guys also like to waste time like me. Imagine what is this? I used to. Okay, stopwatch and let me set up first. Okay, it's 1 2 3 go. Oh, I take more than 1 minute. Way long. Yeah, I always write my code on them. Well, I mean, I have been using it because I thought it looks cool. That's the only reason. I still struggle with them, but I find it cool. Okay, so this is it. This is the Fenwick tree. And again, what I did here was I generally use zero-based indexing in my code. Even if you saw my code, I always use zero-based indexing. I never use one-based indexing. So whenever I create update and query functions, I create them based on zero-based indexing. So I add one so to make them one-based indexing because when we created Fenwick tree, we were taking elements from one, not from zero, because zero is redundant because the largest power of two that divides zero is infinity. Because I mean it's yeah much faster than segmentary, and you see the size of code as well. I created this function just for just because just because I have it every time for because this function this is not even necessary. The size of the code is like very and I choose to create like a template because I use this template as well in normal. If I do, this is the template I use, and just a bit more spacing, but this is the template I use, exactly this. So this was Fenwick tree. Again, for update part, we move to our parent. In the parent of n is n plus n and minus n, the largest power of two, and we move back in query as given for the power of twos from lower. So does anybody that thinks that they don't understand it leave? So everybody understood it, right? The implementation as well. Even though this looks a bit crazy right now, for to you, you will think that okay, what a noob later. For increment in update part, sum use index is equals to index or index plus one. I think that does the same thing that I did, most likely. I don't know how they use index or index plus one. Seems very. I think this is wrong. This should. But is this wrong? Let me think about it. Okay, whoever uses this is it's slower. I'm pretty sure it's slower, but because this should be log square n, not log n. What happens here is index or index plus one. Whenever you do so something like you are suppose 1001. Let's visualize it. What you did was so for let's move try to move from 8 to its parent 16. Okay. What you did was you are able to move in one move. Okay. What they did was they did 8 or 9. So they go from 8 to 9. 8 or 9 is 9. Then go from 9 to 13 or 9 to like whatever it was 12 or what was it 3 plus 8 11. They move from 9 to 11. Okay, then they add one again and they move to 12. Okay, then I think they do something like this again, and it takes around log of n moves to just go from 8 to 16. I think this should be slower, but I think maybe asymptotically this is fast enough. Not sure, but it definitely feels like it should be slower. If generally uses it or tourist uses it, it's faster. Use it. I mean, but I don't think that this is. It's very confusing actually. Very much. Recently, I had a code where I optimized the constant factor from like I only optimized the constant factor. I did not optimize complexity, and my code went from like 6 seconds, 7 seconds down to like 2.5 seconds. And I only optimized constant factor. I did not change anything else in the code. I did not change my implementation much. I mean, I did change my implementation to make a better constant factor, but you should always think about constant factor too. But again, this update looks bad complexity wise to me. I don't know for what David mentioned. I actually don't know how this works. Maybe this is fast enough if you have like all the queries together, but again, doesn't seem like that's the case to me. Okay, so everybody understood Fenwick tree, right? Give me a big yes, then we will move on to the second biggest thing is sparse tables. Everybody understood. I don't know. I have to assume yes. Okay. I feel Fenwick tree might not look as scary now. Maybe the bit magic was. Okay. So let's move on to the sparse table. Okay. So what sparse table can do is it can provide you range. So I only know two things from sparse table mainly: range min query and range max query. Okay. Sparse tables don't provide anything else for a very simple reason. First of all, their complexity will be bad if they provide anything else. You cannot update, by the way. Update is not possible in sparse table because update will be n log n, not log n log n. So if you have q updates, it will be q n log n. So update is not possible in sparse table. And okay, so but why sparse table? Why do we need to run in sparse tables if they are so bad? They can't even do update. So bad, like we have segment tree, it can do update as well, query as well. So sparse tables come into play when you have to calculate range minimum or range maximum in big O of 1. That's how strong sparse tables are. So for complexity wise, we will say that sparse tables are big O of 1 range query for minimum and maximum. If there is any function like minimum and maximum, for example, GCD is similar to minimum and maximum, you can do GCD with sparse table. But again, I don't think it will be recommended to do GCD from a sparse table. Segment tree should be fine as well. But if you have to do some GCD with sparse table, you can do it. Because the thing is, repeating elements in your query does not worsen your query. For example, you have query of 1, 2, 3. Okay. I can do this query. If I do some query, 1 plus 2 and 2 plus 3, and I add them, what will happen to me? I will get an extra value from here. Okay, then I have to remove it. Then I have to query for this again. It will go log and query again, which is useless because I have segment tree that does same thing in log and query, and it does not even have like n log n memory. It has just big O of n memory. Even Fenwick tree does that in big O of n memory. So sparse tables are only useful when min max, GCD, or maybe functions like this, where you can repeat some element in the middle. Okay. So now, how do sparse tables actually work? Okay. So sparse tables store information very. I mean, it's very amazing that again we have binary here. I did not ever relate to binary as sparse table. So okay. So for each index I, I store previous. Okay, let's solve min query. We can solve max and GCD in the same way. Okay, so there is no difference between min max and everything. But okay, and another thing is we can also get index for the element here easily in big of one itself. Okay, so at every index I store numbers from 2 to power 0 in the left, 2 to power 1 in the left, in binary format, 2 to power 2 in the left. Okay, answer for these values. Okay, so for example, you have an array 1, 2, 3, 4, 5, 6. So this element has answer for like itself. I mean before it, but it will be only there's only one element before it, so it will have answer for itself only before it, and we can do this with three ranges only because again 6 is the main one. So 5 has elements of 5, 5, 4, 5, 2. So we can say that every index stores information. Index stores log n values. Everybody understood that, right? Give me a yes if you understand it. Lo- every index needs login memory. Yes. Okay. Again, I will urge you to say no. I mean, you are here to learn anyway. So just say no if you don't understand it. So again, you need login information only. Okay. So now what is your information like? Okay. We need to query index as well, and we need to query minimum as well. What if we store the index of minimum element in this query, in this index? Because if we have index of minimum element here, then I can get the minimum element, yes or no? Again asking for yes or no, by the way. I mean, old yeses are very bad. Yes. Okay. Thanks. So we have indexes for every element. So by storing indexes, so this is what I store for this, the minimum index for this, the minimum index, and in this range. So suppose give me another array, by the way. Guys, another array, please, fast. 274138. Genius. Okay, 573243 seems like a better array to me because it has a duplicate element as well. I mean, in duplicate case, you can handle it that you need right element or left element based on greater than, equal to, or less than. I mean, but again, any index is suffice for you because you only need minimum element anyways. Okay, so what was the array? 573 243. 573 243. So we have an n log n table we have to create. Very sad that we have to create it, but what can we do? We will tell how to create it, but again we so for 5 every index will be itself because there is nothing here. We can imagine that it's infinity because we need minimum, but these indexes are negligible for me. So this is 1 2 3 5 6. Okay, and this is 0 1 2 2 की power 0 elements before me. Okay, so answer will be index 1 itself here, answer will be 1 here, answer will be 1 here. Okay. For 7, answer will be 1 here. Answer will be 2 here because only one element is considered. Then answer will be 1 here because these elements are considered. Then answer will be 1 here, right? Again, I will go, then answer will be 3 here, 3 here, and 3 here. You see, nothing updates it. Then answer will be 4 here, 4 here, 4 here. For this 5, answer will be like 5 here, 4 here, and 4 here. Correct me if I'm wrong. I have been wrong on like more than just multiple occasions. 6. Then this is 6. This is 6. And if we want the first index, then we can do something like a here 3 for the minimum. You can do that with by handling less than handling the symbols. We are calculating the okay. We are calculating the index of the minimum 2 की power 2 element ending at this 3. Minimum 2 की power 2 element, minimum 2 की power 1 element, 2 की power 0 element. For example, for each of them, the index of the minimum element that they store, one element that is stored before them, it's themselves because there is no other element with them. So it is 1 2 3 4 5 6. So index of the second minimum element that they store before them, it's 1 1 3 4 4 6, something like that. I mean, this two elements. 7 has 5 7 5. 5 is smaller. Then I take this index for 3 and 7. 3 is smaller, so I take 3's index here. For 5 and this, we only take 5 because there was nothing before it. Do you understand what is this table, by the way? So I will explain what is this table again. This table is for each index I, comma x. X is the power of 2 की power x. I, comma 2 की power x is the minimum index of min element. Last 2 की power x min elements for I. So what will be those? I minus 2 की power x plus 1, comma I. This will be the range, right? Yes. So we have to fill the index here. So that's how I'm filling the table. I'm not giving you any algo to fill the table right now. I'm just giving you this is what we are storing. All of you understand that? Clear, right? Right. If it's a no, give me a no very fast. Otherwise, I am switching tab. Okay. So now algo will be very simple because you can use 2 power 0 to calculate for 2 power 1. You can use 2 power 1 to calculate for 2 power 2 because again merging two ranges is very easy. Like 2 power 0, you merge two power 0 ranges, you get 2 power 1. This is just a hint. This is not an algorithm yet. Okay, so now we come down to the algorithm itself now. Anyways, so let's see. So for 2 power 0, I hold index of this, and this, right? So for 2 power 1, if I use this and this, I can calculate for 2. If I use this and this, I can calculate this. If I use this and this, I can calculate this, right? Because you have two ranges of 2 to the power x. This range, and again where this and another range starts, 2 to the power x. If I combine these ranges and I combine their answer somehow, then I have a 2 to the power x plus 1. You add them, you get 2 into 2 to the power x, 2 to the power 1. We know that a की power c, a की power x into a की power y was a की power x plus y, right? So 2 to the power x plus 1, and you get the answer for the next bit. Is that clear to everyone? Yes, 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 yes. How does query look like? How does query look like? So, for example, I have to query from 2 to 4, but I only have like 2 to the power x elements. How am I querying for 2 to 4? And that too in big of 1. Big of log n is very interesting, very easy, because you can just erase this again, just like Fenwick tree. You erase the largest bit and move to the smallest bit. Maybe not Fenwick tree, maybe binary lifting. But again, we have to do it in big O of 1. So what can we do is, let's calculate the largest power of 2, 3, 4. There are three elements in 2 to 4. Largest power from all of the number of elements is 2 to the power 1. Okay. So what I can do is, I can take first 2 to the power 1 elements and the last 2 to the power 1 elements, because let 2 to the power L be the largest, largest bit of A. Then I can say that 2 into 2 to the power L is greater than, equal, greater than A, not even equal, greater than A, always greater than A. Yes or no? Not even yes, you understand or no? How this happens? Yes, yes, yes. Because this simply has more digits. Any number with more digits is greater. So I'm saying that let 2 to the power L be the largest bit of A. So I'm saying that 2 into 2 to the power L is greater, always greater than A. So what is A? 1, 0, something below me. And what is this number? This is 1, 0, 0, 0, 0, 0. Add the first bit. This becomes greater. So this element is definitely greater, because this is just more digits. Again, if I ask you to compare 10 ki power 10 to 99, which is greater? 10 ki power 10 is greater. It has more digits. It just has more digits. Any number with more digits in any base will be greater. It's not just base 2, it's any base. Is that clear? Yes or no? Maybe 10 or 100 was a bad move, 10 power 2, because 100 has more digits. Even though 99 has like some expensive digits, but 100 just has more digits, so it is definitely greater. Yes, clear, clear. Nice. I can pursue my career in teaching. Okay. So we can say that this range will be intersecting always. Can we say that now? That this range, the first 2 to the power x elements, the last 2 to the power x elements, this range is always intersecting, because there are more elements in combined this range than the range itself, L2R. Right? Give me a yes if you think that this will always be intersecting. Okay, give me a no if you think that this will never be intersecting. This will always be intersecting, right? We just proved that the number of elements are greater here. So this will always be intersecting like that. You can even see that using the simple pigeonhole principle, because from last to first, there are some elements from first to last. So in some middle elements will be intersecting, right? There cannot be a gap in the middle element. I am saying that for suppose 2 to 4 was my range. Okay, let me go over to some other place. So my range was 2 to 4, 2, 3, 4. This was my range. They're large. So there are three elements. Three. The largest power is 2. So what I can do is I can take this range and I can take this range. And I can take the minimum among these two ranges. That will be my answer. Because we were storing the power of 2's, right? So we can query the power of 2's in big O of 1. So this range, and this will always be intersecting, because this is what makes largest bit of 2. Okay, and we proved that before that there will be more elements. So I am taking first some previous sum range, last sum range. So it will always be intersecting, because I if I say that some there is a gap in the middle. Suppose there is some element that was left, then this range plus this elements plus this range should be like equal to the elements. So these two ranges addition should be less than equal to the number of elements 3. But that is contradicting our statement that they are always greater. Got it right? It just got a bit more mathy. I hate it now. Now we have to go to query. Okay, we are on query anyways. So let's just see. 2, 3, 4. Okay, not this pen. 3, 4. Okay, so if I take this, so I can take the best among these two anyways, right? So what is the minimum in this range? What is the minimum in this range? Compare them. Take the best. Understood, everyone? If everyone understands, I will go to the implementation now. I will implement it. Okay, everyone understands, right? Okay, great. Now let's move on to the implementation. I'm not going to do stopwatch now, because this is, I mean, I'm not very confident with. I mean, I don't really need type name here, because I can just use long every time, but it's still, it is better to use it. I generally name it RMQ because of habit, but you can name it sparse table as well. I will name it sparse table now. So table. Okay, what is the max bit required? What is n? Again, very standard. Sorry, I can do T here or A here. I mean anything works. I think T would be better again. And we need vector T A. So I can do this P, because I also need the values to get the minimum to compare them. Then it's equals to B is equals to A dot size. Okay, while bit, if somebody doesn't understand it, they don't really need to. This just calculates smallest power, smallest 2 to power max bit greater than n, and from then 0 to max bit minus 1 will be what I require. Okay, Okay. Then we, as we said that, then for the first few elements, we said that, right, the table of I of 0 is I because only one element is there. Then it's the minimum of itself, right? So now let's go from, okay, what I need is now, okay, so for I comma 2 to power bit, 2 to power b, I need I comma 2 to power b minus 1 and I minus 2 to power b minus 1 comma 2 to power b minus 1. These two ranges to combine. Yes, give me yes. I'm skeptical to use that. Most of the time, I'm not sure about the accuracy of this. Like, I mean, it might give you correct value every time, but it's fine. I mean, here you are already going to use a much more costlier operation. This will not even be like a simple part. Again, I can use something very. From now on, after this, I will use a very interesting trick to use to calculate the larger power of two. The trick is something like this. The trick uses 32 minus under the built-in count leading zeros. So any of you knows count leading zero function, built-in count leading zeros. So it gives you count leading zeros in the, it will give you leading zeros after your first bit. And you can use 32 minus 32 minus built-in count leading zeros to get the like first bit. This is much faster than even underscore underscore login, I think. Yeah, number starting zeros. But if you minus from 32, then yeah, this will. Yeah, this should have been told in bit manipulation class. I think this is one of the most standard things that is used. I mean, I could even use that here, but I didn't use that because I mean, I don't want to remember everything like this. I mean, it was unnecessary there. I mean, we don't need to optimize there much. Okay, so we need to use these bits. So let's go. We are at bit. So if I is greater than equal to this, now I should be greater than equal to this. Otherwise, for this range when combining, suppose you are at the one element and you are combining this ranges. This is nothing, right? You are combining with nothing. Then you can just you store your own answer already. You don't need to change your answer here, right? And A of table of, hmm, maybe I can use something. Okay, I thought I was missing something. Is less than. I mean, you can use 2 to power using left shift operation, I think, I believe. So this should be pretty much clear by the statements themselves, how we created them. You will be using int there. You can always force yourself to use int. If you have int define long long, then you can use count leading 0 ll like clzll. That is also a function. That is also a choice. But I don't have int define long long, and I don't usually define int to long long. I like try to use normally int 64 or long long themselves in the code. So for me, it works very smoothly. I mean, generally you should have a practice like that as well. So we have int query index. Let's say you want query index. What is query index here? The for min this was a min sparse table. So it will be min element index. So again, int p is equals to like the bit, it will be 31 minus 0. But for this to work, you have to know that L is less than equal to R, right? So you can put maybe assert, or if L is greater than R, return -1. And you can say that return A of table of like R minus P. No, it should be L plus 1 or P minus 1 of P is greater than A of table of R of P. Then okay, table of R of P else table of plus 1 or minus 1 of. Is that clear? Give me a yes if it is. Okay. It's just the shifts. Whenever I write a shift, right, I try to just think 1 or P minus 1. I try to visualize this as 2 or P minus 1. This becomes easier. I don't think we will need break because we are almost done. I mean, with the agenda. Yeah, I mean, you guys understood Fenwick tree. That's the like the top class in bits, and you are afraid of this. I mean, if you actually understood Fenwick tree in like the just one session, right? Then this is like you guys are actually, I mean, geniuses. I mean, it was very hard for me. I had to take like many like tutorials. I had to read many tutorials for that. So this is it. You can just try to visualize it. For example, if I is less than 2 ki power bit minus 1, then we can't query for the previous section, right? The previous section is unnecessary in that case. Okay, and we are just trying to. Yeah, implementation of Sparse is definitely tougher than bit. If you understand bit, right, it is just easy. But implementation, but Sparse table is a lot easier to visualize. There are two things in implementation that comes down. One is if you can remember Fenwick tree, you can write it very fast. If you remember like sparse table, you will still be slow because there are many things to take care of. Many out of, like when you are doing shift operations, there can be out of order. Like you can have negative elements. You never know. So this is just again very difficult to predict. So you will never know. But again, if you visualized it correctly, right, then if you understood what I did in entire part, then this should be very easy for you. And query value is the just the like value of the index that you get from query index. By the way, I might just use this as my implementation of Sparse table. I currently don't have any. Which if statement? This one. Okay, I will go through them on a drawing rather than the code. So what happens is there are two cases. So first of all, suppose you are at some index I, and this is 1 to I, and again you are calculating for bit B. Suppose for bit B minus 1, you go out of the range. Then you have to combine this range. This range was completely outside, right? And did you calculate for negative indexes? You never calculated for negative indexes. And this is just redundant anyways. You only need answer for this. So you won't update in that case. Okay. And in so I'm saying that just take answer for this bit for now. Okay. And then let's try to update it later. Okay. Even in my code, I did that. Just take answer for the previous bit minus one. Then we will try to update it here using the if else case. Okay. We were used to introducing a min segment. So in second example is I'm at I. This is one. So this is the ranges. So okay. So which range has a smaller element should be my answer, right? Yes or no? Okay. And by default, I put this as my answer. So I will update it to this if this has a smaller element. You can see that. By default, I put this as my answer. And if this index has a smaller element, if A is the array of elements, see here. For B, I copied it to A because I need this here in query value as well. That's why I had to copy it. So if this has a smaller element, then I will change my value to this, may change my index to this. Yes, right. So you understand it, right? Now we have the min index for each power of 2. Then the query should be simple as well. Whichever has the smaller element should be the answer. If table of RP has smaller element, then this should be the answer. Otherwise, this should be the answer. Is it clear to everyone? Give me a big yes. Okay, yes, yes, yes. Nice. Do you know why this is so good? Like why sparse tables are so good? Again, this is not my you can actually do query for LCA in big O of 1 using a sparse table. Like if some of you know how sparse table works, you can look at some blog about it. Querying for it in big O of 1 using sparse table. You can actually do it in big O of 1. And the more crazy part is you can actually do it in big O of n and cross big O of 1. But big O of n cross big O of 1 part is very, I would say, impossible, more or less. Okay, so everyone, it's clear, right? Any questions? Anything? Yeah, LC in big O of 1 exists. You can search about it. I think uh, maybe I will ask someone to share the blog later. Okay, Dhruvil, just, I mean, for you, I think it will be a lot more easier. Josh, I don't know Josh. I mean, eh, maybe I might know his CF handle. If it's Josh, CF handle as well, I don't know. How to reach GM? I mean, the funny thing is, I only reached GM once and I fell and I never became GM again. So I don't think I'm the best person to answer that. Maybe just get lucky. I mean, until IM, it is not very. I was not lucky for IM, but for GM, I think that was very lucky for me. I mean, that contest was just all the stars aligning and me giving my best at the day. Just get lucky for IM, then get lucky for GM. Get lucky 2 times in a row. Oh, I explained fan victory. That was the whole point for this class to understand fan victory. And you are saying you don't understand it. You are hurting me like in 100 different ways right now. Yeah, I was saying that he's very close to IM. No, I mean, I think that once you reach certain rating, that rating is not very appealing to you after that. Then you can reach it again. If you can reach it once, you can reach it again. I personally believe that, and I think CM should be like easier maybe right now. I think Div 2s are very crazy guessing these days. Maybe I'm wrong. Maybe I haven't been giving Div 2s much, but I think more of a guessing part has come these days. But yeah, you will improve. I mean, it's fine. I was also a specialist. I mean, if you see my profile, I was struggling in specialist expert for a long time. I mean, we can always debate that, but uh, most of the time, my strategy is, does this make sense to me? I mean, if this makes sense to me, I think most likely this will be correct. If this makes sense to me and this is wrong, then I can't solve this problem. Or maybe something else makes more sense later. How to thanks, David. How to improve for div 2D? Solve div 2D, man. I mean that's the whole point of the problems. Like if you want to be able to solve div 2D, then solve more of div 2Ds. Then you will be able to become good enough. I mean that's not your fault mostly. I mean I think yesterday's contest was a pretty crazy side. Problems didn't have much ideas until F, I think. Until F, the problems were pretty much guessable very easily. But again, if you want to be able, as I mentioned, if you want to get to certain level, then you should try to solve the problems at that level. And you will get a much better idea. So around when I CM'd, I think I used to do a lot of duels with certain people, and we duel like random 1800, 1900s because it was also fun. No, someone said that they still want to black box Fenwick tree. I don't think the session was as nice. No, like don't black box Fenwick tree, by the way. If you black box it, right, you will never be able to understand it and you might still use it as black box again and again. There is a very nice problem on Fenwick tree, by the way. If you just understand Fenwick tree, right, how Fenwick tree works, how update works, you can solve that problem. Not just how Fenwick tree works, but again, there is a one more idea after that. But The main idea of the problem was how Fenwick tree works, and the problem is literally named Fenwick tree. And it was just you had to know that how update actually works. Maybe you can try that problem, but yeah, rewatch and try to understand. I mean, you see, you can black box many things, but understanding something gives you a much deeper idea. So, for example, until now, I had black boxed, like, I will give you my example from yesterday's contest, not even that far from yesterday's one. I had black boxed Eulerian path. So F spoilers, major spoilers. F was Eulerian path. I had black boxed Eulerian path. I never knew how to implement it. I never knew how it works. Okay, but when I but I just copied it and it was wrong. And I was trying to debug something else. I was trying to debug that my idea is wrong, maybe. So I was trying to debug my idea. My idea was correct, but because I black boxed something and I copied it blindly, I got WA. I mean, it happens. If I understood that, I mean, if I understood the like Eulerian path, then I would be able to implement it within like minutes because the problem did not have very hard implementation, or it does not have very hard implementation. I can try to understand Eulerian path. I mean, I will try to understand now, but black box means that you know what an algo does, but you don't know how to implement that algo or how to like write code for that, or like you don't internally understand it. For example, you know Fenwick tree can do prefix sum query, and you can use prefix sum query to do range sum query. But you don't know how you update in Fenwick tree or how you query in Fenwick tree. So black boxing is bad. Again, it might work for someone, but it will not be a very good practice in the long run. Yesterday's contest, I think I pretty much guessed every problem from A to F. I mean, F, I actually solved it, but again, okay, thank you guys. Any tips for getting to 1600? Practice, matlab, only practice. I mean, there is nothing else other than practicing and enjoying it. I mean, if you enjoy it, you will be like grasping more things from it. So again, like remember to enjoy it. Don't do it for the sake of doing it. Like, don't think of it as a chore. Don't think of it as your college studies. I mean, I think uh, cheating at this time has always increased. I mean, it was always an issue at this time of the year. I mean, even when I started CP, at this moment the cheating increased. The main reason cheating increases at this time is everyone thinks that you can get placement by cheating. But and the first year, I think the main cheaters are the first year students mainly who are going from first year to second year because they know that they want need to do CP to get placement later, so they try to cheat in CP to get a higher rating. And at this time, like I think there are many things that happen at this time. So there are, uh, I mean, I can only guess their mentality. There are many other newcomers joining, so they also want to boast it. Okay, that see, I have such a high rating. I mean, this is just I mean, trying to like flex something. It doesn't help. Cheating is not bad for them. I mean, cheating is not bad for you. It's bad for them. You just need to like improve. You just need to like focus on your improvement. I mean, again, it might be demotivating. It will be. I mean, it will be demotivating to see yourself below in a rank list where you could be much higher. I mean, I won't say that they have hybrid so much. I mean, many. I think it is not the issue for with the influencers. It is the issue with the student themselves because again, demotivation and like demotivation can lead to like your much more stress than we can imagine. And again, those who like give time to CP and they're trying to improve, they might be feeling much more demotivated. But again, it is not a thing to be demotivated about. If you are giving time to something, you will get returns. So, like, just don't be demotivated about anything. It's I mean, it's going to change again. I mean, the colleges will start again. They will again forget about CP and just try to enjoy their hostel life again. Just try to enjoy their college again, and they won't even know when contest happens most of the time, and they will leave CP. I mean, easily. I think it just repeats at this time of the year. Even in my batch, when I was from first to second year, it increased around this time as well. I mean, if you are using GPT to write a CP code, I mean, it's fine. But I mean, you might get like flagged. But apart from that, it is fine as long as like you are not taking help from someone or something other than like a pre-written code. It's fine. I mean, I also try to like keep that as a benchmark for myself. So, for example, I try to keep a benchmark that until I solve this many problems, I will not look at rank list because I look at rank list too much. I try to look at like what others are solving. I mean, I'm not. It's a very bad habit of me. I think I have always like many times I have given up on some problems that I could solve. Actually, thanks, Avas. I have actually cheesed many problems using this LCA trick with Big of Fun. Yeah, try to like get rid of it. I'm also trying to get rid of this habit. For the last contest, I actually only looked at rank list once, so I'm very happy. I was trying to think of this project that whenever a contest is ongoing, maybe there is some context in web. Try to create an extension that blocks the standings. I was trying to think of this project. Like when a contest is ongoing, there is no like there's a contest ends in timer, right? So you can get from there this context that the contest is still ongoing and you can block the rank list. Looking at it in the middle of the contest is not your standing. I mean, the first 15 or 30 minutes won't determine where you will stand. And again, at the end of the day, standings and the ranking is reality where you stand. I mean, I disagree with this. Matlab, it's fine. You are not competing with others. You are competing with yourself, honestly. I try to like also I try to think of this, but again I'm not able to follow it myself. So this will be hypocrisy if I try to defend it that you have to focus on improving yourself rather than looking at rank list because I look at rank list myself. But still focus on improving yourself. If you for me it's more fun to solve harder problems than to solve like a more problems and get a good rank. I then why don't I start from the back because I don't know like will I be able to solve this problem or not because that problem is probably like very hard to solve and I can't solve it in next 2 hours probably. I don't know. Ask IICPC team. I think the camp is great. You can just come back to look at these lectures anytime. I think this will be a good material, addition to good material on internet. You can ask IICPC team. I mean, I don't know what they're planning. They ask Dhruvil. Dhruvil knows what they're planning. Not really. Getting better rank is not you improving. I mean, my rank fluctuates. My rank fluctuates between like 200 to 500. It doesn't mean that one day I like my intellectual ability decreased and one day it increased. It doesn't work like that. You will know when you improve. You will know that you are able to think things more thoroughly and you are more calm in harder problems and you're better in this type of problems now that you were worse before. I mean, I you should go ABC. Again, even if you don't care about ranks, at the end of the day, standings, like, you can flex them. I used to flex a lot my standings in college. Yes, as Dhrubil mentioned, solving one more problem and solving problem lesser to sign is a sign of improvement. So what happens is the graph is very steep for CP. The improvement comes at a very like shocking rate and it just steeps down again. You are not improving for a very long time. You improve like very much, then you stop improving for a very long time. I mean, you inside yourself you will know that you are improving. I mean, I always knew that I was getting better whenever, even if I had a very steep curve at some point. What is Bangalore reservation? I haven't heard the news. But Tech Park is in Hyderabad and like Pune and Gurgaon too. 75%, damn. 75% seats to Bangaloreans, like the people in Bangalore. If it happens, the tech will leave Bangalore, most probably. I mean, most companies would require best of the best anyways in them. They won't take reservation as anything. Yes, government jobs are the best. As Dhruvil mentioned, participate in each and every contest. Never fear drop. Like, if you reach this rating again, you can reach it again. Always have this mindset. So you don't have to fear that you will not reach this rating again. Funnily enough, maybe I should have had this mindset that I cannot reach this rating again because I never did. But yeah, I mean, you should never actually fear giving contests. I enjoy giving contests. Virtual contests are best practice. Yes, I mean, for me, virtual contests don't actually give me the feel. I'm not hyped in virtual contests, so I try to avoid virtual. Instead of virtual contests, I try to give every contest possible that I can give because the contests give me the So in virtual contest, you know the time is ticking, but you are not serious about it because this is not an actual contest. Nobody's actually participating. They all participated like years ago. For me, I get a thrill when I do real contest, and I like the thrill of that. So that's why I do CP very regularly. I mean, I try to solve more problems, but again, I end up giving up because I can't. Yeah, adrenaline rush is just more addicting than like anything, even alcohol. Okay, guys, I will end this now. I think we were going to end it like 20 minutes ago. We have been talking for 20 minutes. Okay, guys, thank you all. And I loved the audience as well. The communication that like you guys were very responsive and it was two-way. Thank you, everyone. Bye.